In this video, we'll take a look at electrophilic aromatic substitution, or EAS for short. So these reactions involve a hydrogen atom that is on an aromatic ring and is replaced by an electrophile. So that scheme appears like this. You have a benzene in this general example here, and some electrophile. Now, the identity of this electrophile can vary, but very commonly it's going to have a positive charge, and if not a positive charge, it's going to be very electrophilic for some other reason. But those electrophiles can then be substituted with a hydrogen, and you effectively replace this hydrogen with the electrophile, and you lose that hydrogen as a byproduct. Now, mechanistically, there are many ways that this hydrogen can leave, but effectively the reaction is replacing that hydrogen with an electrophile, which is why we call it a substitution. Now, mechanistically, there are generally three steps. So first, you have to generate the electrophile. If this is necessary, sometimes the electrophile can already be provided without a mechanistic step that is required for that. It depends on the type of electrophile that you're looking at. So sometimes you need step one, sometimes not. But always you're going to have an electrophilic addition step. This is step 2, which breaks the aromaticity, which makes it the slow step. And thirdly, there's going to be then an acid-base reaction, which will reform the aromaticity. So if we look at a very broad example here, we can have hydrogen or a benzene hydrogen, for example, that is shown. And what happens, I'm skipping the generation of electrophile. We're just saying that there is an electrophile here. We'll get into specific details where you may need to generate the electrophile. But in any case, your first step here that we're showing is an electrophilic addition, where you use the pi bond here as a nucleophile that attacks the electrophile, and thus breaking that bond to form the carbon electrophile bond. That is this pink bond here. And this also forms a carbocation as the other carbon of the double bond. Now, this is the slow step because it breaks the aromaticity of the benzene, the aromatic ring that we start with. This is very unfavorable. So there are many reasons, many ways that you can help this step along to make it feasible for reactions, but this is always a slow step in any case. Additionally, it's important to note that there is resonance stabilization by these conjugated double bonds here. There's 2 double bonds in conjugation, so you can have a total of 3 resonance structures to stabilize this positive charge. But that still doesn't make this a very favorable step because you're breaking aromaticity. And remember, aromaticity is an extremely stabilizing feature that does not want to break if possible. So that explains why this is a slow step. And then lastly, we have this acid-base step that reforms the aromaticity. The identity of this base can vary a lot. It doesn't necessarily have to have a negative charge, but as a general example, I'm showing it, have one, and then we use the base to attack this proton, which is now extremely acidic, because when you remove the proton, you can reform the aromaticity, which is why this is extremely fast. So this base will form a bond to the hydrogen, simultaneously cleaving that bond onto the carbon to essentially form the carbon-carbon double bond, which reforms the aromaticity. So a byproduct here that I haven't drawn that is there is the base bound to the hydrogen. Again, the identity of the base will determine what BH is. All right, so here we have a question. We are asked to draw a detailed mechanism that predicts the product. So once again, we have benzene, and we have now a halogen and a catalyst. So this is likely electrophilic aromatic substitution. And let's recall the first step of the mechanism is to generate the electrophile if that is possible. So if we look, or if that's necessary, I should say. So if we look at these molecules, chlorine, molecular chlorine, Cl2, and aluminum trichloride, we don't see any obvious electrophile right away. So we are going to have to generate it, and it is through the following mechanism, where you have molecular chlorine and aluminum chloride. Aluminum chloride is a Lewis acid. It can take a new bond, and we have chlorine, molecular chlorine with all these lone pairs that can function as a Lewis base. So this first step in the generation of the electrophile for this specific example is a Lewis acid base reaction where the chlorine binds to the aluminum. So when this happens, this simply just forms a chlorine-aluminum bond, like so. And now we have to consider charges. So we've added an extra electron to the aluminum, so this has a negative charge, and we have effectively gotten rid of an electron because we are using both electrons to form this new bond. So in our formal charge counting, we'll have a positive charge on this chlorine. Now, once this occurs, there is a big driving force to stabilize this molecule. So what happens is this bond cleaves onto the chlorine, which will stabilize that charge and split this into two molecules, which is entropically driven. Entropy favors more molecules. So what this does then is form Cl plus and aluminum tetrachloride now, which has the negative charge still. Now, Cl+, this is our electrophile for our electrophilic aromatic substitution. So that is step 1 of our mechanism. Now, step 2, we have to undergo the electrophilic addition to the benzene, now that we have our electrophile. Right? So here we'll have benzene is our functioning as our nucleophile, that pi bond there. And then we have Cl+ that we just demonstrated how that generates using the aluminum trichloride catalyst. This will attack the chlorine and breaks the aromaticity. Right, so we just created this carbon-chlorine bond. By the way, there is a hydrogen there that I'm going to draw because it's relevant to the next step of the mechanism. But this hydrogen is this one here. That was present initially. Now I'm showing it. And then we're breaking that bond, so we put a carbocation now to the other carbon involved in the double bond. Okay, so now at this step we have the carbocation. This is resonance stabilized again because of the conjugated double bonds, and we have aluminum tetrachloride floating around. So the last step now is our Lewis acid-base reaction to reform the aromaticity. So I'm just going to abbreviate it acid-base to reform aromaticity. Again, which is a big driving force, which is why this step 2 here was the slow step, because we broke the aromaticity in that mechanistic step. So now we have an acid-base reaction. Again, this proton here is extremely acidic because if we remove that proton, we will reform the aromaticity. So we have a Lewis base in the aluminum tetrachloride. Now, this is an interesting part here because the chlorine actually is going to function as a base. Many of you might think the aluminum functions as a base, but that negative charge on the aluminum, there's not actually a lone pair there. It's only a negative charge from all the 4 bonds that are involved in the aluminum's molecular geometry, and that is why the chlorine functions as a base, because it can essentially use this bond to form a chlorine hydrogen bond, forming HCl. And then again, we will cleave this carbon hydrogen bond to reform the aromaticity, which is why this is a very favorable step. So what has happened is you've reformed the aromaticity with the chlorine now instead of the hydrogen, and then you've created HCl and aluminum trichloride. It's very important to form aluminum trichloride because if you didn't, it wouldn't function as a catalyst. And it's important to know that the aluminum trichloride is catalytic. Now, you may wonder why this doesn't react simply with like HCl. Like we've looked at with other alkenes, that electrophilic addition can occur with HCl. So basically, why doesn't this step happen? Why do we have to go through the generation of the Cl+ instead of doing this? Well, the reason is breaking the aromaticity here is not favored enough for this to happen. When we have the Cl+ floating around, that is a much better electrophile than the hydrogen on HCl. So in essence, That is why we have to go through this more extended mechanism, and we need the addition of the catalyst to have this reaction occur, because without this does not happen because the electrophile is not sufficiently electrophilic. All right, so here we have another question. We're asked to draw a detailed mechanism that predicts the product again. And here we have benzene and nitric acid and sulfuric acid. So once again, we're going to have an electrophilic aromatic substitution. And as we just looked at, HCl did not have a sufficiently electrophilic hydrogen. So this is a similar argument here with nitric acid and sulfuric acid. We are going to have to start by generating a stronger electrophile to initiate this process. So we have to generate our electrophile. That is step one of the mechanism. So let's start by drawing the structures of nitric acid and sulfuric acid. Again, the hydrogens aren't shown here, or excuse me, the hydrogens are shown, but the lone pairs are not. They're implied by the charges. So this is nitric acid, and then let's draw sulfuric acid. That has this structure here. And now the first thing that happens is we have the lone pair on this oxygen of the nitric acid that will attack the acidic proton in sulfuric acid, and this will cleave to form the conjugate base in a standard Lewis acid, Lewis base type reaction. You may wonder why a lone pair on this oxygen over here isn't attacking, and well, there's two reasons. One, it has resonance up into this other oxygen here, which makes it so this is less basic. But additionally, you cannot generate the most reactive electrophile with using any of the other oxygens. So those 2 points together is why you have to attack with this oxygen first. So what this yields is protonated nitric acid. And then HSO4 minus. I'm not going to show the whole structure here because it's not critical for this part of the mechanism. So now what happens is we have water. Water is an excellent leaving group. So internally, this lone pair now will form a nitrogen-oxygen double bond. Oops, I missed a positive charge here, right? That positive charge started there. It stays in this molecule. And now, then we reform this oxygen-nitrogen double bond, and then we cleave water at the same time. So what this forms is NO2 plus, right? NO2 plus, and then water as a byproduct, which I'll just draw minus H2O. This now is our extremely strong electrophile that will undergo the electrophilic aromatic substitution. So now we need to move to our electrophilic addition step. This is step 2. Okay, so electrophilic addition. So again, we have benzene. The double bond here is going to function as a nucleophile. And now we have our nitric acid, NO2, or the electrophile generated from nitric acid, NO2 plus. This pi bond attacks as a nucleophile, and we cleave this nitrogen-oxygen bond at the same time. You may wonder why we need to do that. If we don't cleave it in a concerted mechanism like this, then we're going to have 5 bonds to nitrogen, and that is not allowed. So that's why this must happen like this. And then we now form NO2 on the benzene and a carbocation. And this is the end of the electrophilic addition step. And now 3, we'll do the acid-base step to reform aromaticity. So I'm just going to abbreviate it heavily this time. Acid-base aromaticity. So we have water floating around. So water is going to function as a base here and remove this acidic proton to reform the aromaticity. So that's what's going to happen. So this reforms the aromaticity while retaining the NO2 group on the benzene. All right, so now if we think about what just happened, we replaced the hydrogen that was here with NO2, and we produce H3O+. And remember, we have HSO4 minus floating around, so it's more than likely that these two will equilibrate back to H2SO4 and water. But that's kind of an aside here. The real point is that we generate this this nitrobenzene, where we've substituted in multiple mechanistic steps a hydrogen with the NO2, right? And by the way, we missed this charge here throughout, but that is critical there. All right, that is all I had planned for this video. I hope you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. If you have a topic suggestion or question, feel free to leave it down in the comment section below, and I'll get to it as soon as I can. So with that, I'll see you all in the next video, and I hope you have a great day.